I love it.
Okay, so we are ready to get started for our final session of the Joint Science Workshop. Thank you all for sticking around. It's been a really, really exciting day and a half. We are about half an hour behind, as you all noticed. I hope you enjoyed the fact that we did give you hour and a half for lunch. And so we are just going to slide a little bit into the poster session. We do have to finish our poster session promptly at 5, but hopefully everybody has had a chance to look at the posters and have those meaningful discussions throughout this morning. Our last session is forward-looking, so we're really going to be inspired by our next 5 speakers on what we should be thinking about in terms of science, technology, and application for the next decade. And this is really important for us at NASA headquarters, because these are the things that we really want to hear from you as our community. So that is food for thought for us to then enable and give you the tools to enact that vision. This session is going to be moderated by our absolutely fabulous Dr. Paula Bontempi. Those of you that have known Paula, So most of you have known Paula when she was at NASA headquarters. She spent 16 years leading the ocean biology and biogeochemistry program. And so if it's a wonderful program, it's because she set it up that way. And if you don't like it, it's because I'm leading it. So it's not her. And she also did a stint as our acting deputy division director. And Paula, we really missed you at NASA. But she's moved on, and she's probably much happier and has a lot more free time. And she's now dean at University of Rhode Island College of Oceanography. Graduate School of Oceanography. Sorry. So Paula, the floor is yours. Thank you.
Thank you, Laura. I'm not as tall as Laura. Okay, I know how it is, everybody, to come into the home stretch of the last afternoon of the meeting. But hopefully what you'll hear this afternoon are some really exciting, as Laura said, forward-looking, in my mind, disruptive research and technological innovative talks. So I'm excited to hear today. So the afternoon session is going to be focused on the Earth and cascading impacts of climate change on our home planet and its ecosystems. And then, of course, ecosystems and Earth system resilience. I just want to pause and recognize that we meet today in College Park in Maryland, the traditional lands of the Piscataway Tribal Nation. I honor their histories and ancestors and perseverance in our communities today as our country was built on Indigenous land. I recognize the historical and continuing impacts of colonization on Indigenous communities, the resilience in the face of colonial and state-sponsored violence. I honor their stewardship of the land, the sea, and those resources that they hold sacred and from which all of us benefit. By the way, the 4th National Climate Assessment from USGCRP in 2018 pointed to and highlighted the disproportionate impact of climate change on Indigenous, low wealth, and urban core populations. The threat is again highlighted in the most recent IPCC and in the one especially on oceans and cryosphere in 2019. And social and environmental justice simply have to be at the core of our climate research and solutions. Now, according to the session description, humanity, all of us, have a great capacity for resilience. And this is through research that we advance our understanding at the fundamental level of global ecosystems, something we've talked about a lot this week. We assess the changes and quantify the changes that are associated with those ecosystems, and then we build that predictive capability for bringing in all of our innovative data streams so we can inform mitigation and adaptation strategies. There are many opportunities to better understand Earth's ecosystems and enable a thriving humanity under Earth's changing climate and the next decade of Earth science. It's up to all of us to make this a reality. So today's talks will also highlight needed investments and opportunities for the U.S., not only in research, but in that innovative technology and modeling. So I'm really honored to be your moderator today. And with that, I will call up our first speaker, Fade Shurayat from the University of Miami, who will talk to us science.
Thank you, Paula and Laura. My name is Faith Triath, and as Paula mentioned, I'll be sharing some new technologies for marine and planetary science. I was 10 years at NASA Ames, and I recently moved to the University of Miami, where I continue to develop a lot of technologies for NASA and also with National Geographic as a partner. Just to give you a bit of background, I'm a recovering astrophysicist. I started off my life in Southern California, really passionate about animals, astronomy, and the ocean. I wanted to reach out and try to touch the stars, and I was fascinated by this idea of detecting planets by looking at the starlight coming from other suns in the solar system, or sorry, beyond our solar system, and looking for dips in the amount of light to detect a planet. I built a telescope in high school where I was homeless for 3 years living on a mountaintop, so it aligned very well with making lots of observations of stars, and it discovered a new exosolar planet about 150 light years away. That got me hooked on science and looking at trying to develop technologies for imaging planets directly as they transited their stars. That led to a technology called atmospheric lensing and got me my first job at NASA as a PhD student, developing these advanced high-resolution imaging systems. I took this image of the sun. Around this time in 2012, I met an oceanographer, Sylvia Earle, who pointed out to me that I've been mapping all of these celestial bodies, and we now know more about the immediate solar system than we do of our own ocean floor. This shocked me as somebody who really cared about the sea and assumed this was done. So I pivoted completely into ocean mapping. And I'm very excited about ocean mapping on Earth because we're not the only ocean now in our solar system even that these have the highest potential for life in my mind, much to the chagrin of my Mars colleagues. We now know of many moons, icy moons of Jupiter and Saturn that are likely to harbor salty oceans underneath an ice crust. So if you're looking for your next vacation spot, I would probably choose one of these because there's high preponderances of water. And this is an effort that, of course, Laura had helped create oceans across the solar system within NASA. I am trying to share from an astronomy background that we need like our Webb Space Telescope moment in oceanography. We have a fleet of amazing satellites. We do not have yet a $14 billion investment in mapping what is perhaps the most important ecosystem to our survival on Earth and the key to our origin story on our home world. So at the University of Miami, I was recruited to direct the Aircraft Center for Earth Studies. That's some of my team that are here in the audience. Dr. Toronto, you heard from earlier. We have 4 main programs in my center, and I'll talk a little bit about the instruments today, FluidCam and MIDAR. These are designed as sensors. We have an aeronautics program where we developed high-altitude platforms as well as helicopters for flying those sensors, a CubeSat program for a path to orbit for many of these technologies, and finally an AI and high-performance computing component where we process data from the instruments. Okay, so first, why is remote sensing of aquatic environments so challenging, and why does an astronomer, make contributions to this field? When you look at the sea, this is what you can see from orbit. This is a Maxar image. The first issue you will all attend with is attenuation, right? There's not much light coming from the ocean. This is a problem you see in astronomy quite often, and the solution is you build a big honking telescope. In aquatic remote sensing, the challenge is really that, within the ocean, a lot of the wavelengths to the right of red, so these are infrared, radio wavelengths, they're all completely absorbed. You're really left with just the visible bands of light, of which the blue and the ultraviolet tend to penetrate the deepest. The second issue is refraction. Ocean wave distortion. You saw some breaking waves in the initial slide. This is where light gets bent as it travels through 2 different fluid media. This is right now the #1 cause for resolution degradation in water. It's also why we cannot repeatedly image an object underwater from satellites or aircraft because you're looking through a refractive surface and that correction has not been applied. So I set out to investigate this at NASA and at Stanford for my PhD. I simulated the environment in a test pool. You can see 2 phenomena that this technology called fluid lensing exploits to image the seafloor. So one is this effect where when waves pass over an object, they will magnify or demagnify the object depending on the shape of the wave. The second is the formation of these bright bands of light called caustics. They can actually exceed the downwelling irradiance at the surface by 1,000 times at depth. So if you track both the caustic and a positive wave event over a region, you can actually see that object at very high resolution and at significant depth. That gave rise to an instrument called FluidCam, which is designed to provide refractive corrections in near real time and then track caustics to see very, very deep in the water column. And the result is when you fly this on aircraft, you can see a multi-rotor drone here. We also fly this on fixed-wing aircraft. We can survey really large areas of coral reefs, which are of particular interest to me in a rapidly changing climate. And now living in Miami, I'm keenly aware of sea level rise. You can see the effects on the sensor side of, in addition to refraction and caustics, you have significant reflections or inverse caustics. And this is what the fluid lensing solution looks like for that environment. So this campaign was done in 2016 in American Samoa and was validated to about 0.5 centimeter resolution across an entire coral reef. The latest results from 2022 are very exciting because for me, it's the first time we could deal with more challenging environments like wave breaking. So this is a contemporaneous image from Maxar's WorldView 2 satellite of a reef in Tumon Bay in Guam. And you can see in the next slide what the fluid lensing view looks like for that same period. So it's the first time we've actually been able to expose a lot of the unique coral taxa that exist on the reef ridge, as well as marine debris that accumulate there. These are very challenging environments to work in, but if you talk to astronomers about signal to noise ratio, this is the regime that we usually operate in. 1 to 10 to the 9 photons is the one that you want. We can now do this for a lot of marine environments, and we're now revealing, in the case of Guam, the entire coral reef to a depth of 65 feet at the centimeter scale. So if you're in Guam and you drop your cell phone somewhere while you're snorkeling anywhere on the island, we can tell you where it is and likely when you dropped it. We can also track when tourists damage coral, when fish get removed from the ecosystem. We can look at change of coral colonies over time. It's really been a completely new way of visiting this reef. The downside, of course, is the data sets are 150 terabytes for each mission because they're 3D reefs at centimeter scale. If you're curious to see some of the data sets yourself, you can check out our online data viewer. I'll show you a preview of what that looks like for Guam. Have a good computer and a good internet connection. You can load up Tumon and then just keep zooming and zooming in until you're at the centimeter scale. You can look at the bathymetry products that are derived for those regions. And then as you heard from my colleague, Dr. Anna Toronto earlier, you can look at the automated habitat assessment that we do using citizen science through NemoNet for all the different coral types, as well as Shannon Index and higher level biodiversity metrics. Recently, we've also been rolling out the detection of what's in the column at the request of many of our colleagues at workshops like this who said, why are you deleting all the fish data? That's what we want. Typically, fluid lensing makes a benthic surface image, but now we can go back to the raw data and actually pull out all of the animals that are moving as a function of the average group lenslet velocity of the surface wave. So in these campaigns, we've also been adapting the models in which we perform science. And with a NASA MURIP grant in Guam for $1 million, we trained 25 drone pilots on island. And now these students are funded every 2 weeks to go with our fleet of aircraft and map their entire reef. So they have precision coral reef management in Guam, and it's really a pilot for what I hope we can replicate elsewhere in the world. At the higher scale, we've been working with NASA to develop high-altitude solar drones. These are 85-foot wingspan aircraft that can fly for 3 months at a time. I like them because they're not satellites that can potentially blow up or deorbit. They can hover over an island and get every photon they can from deep environments, which means we can see, beyond the reef down into the forereef. So FluidCam helps solve that first, photic zone issue for remote sensing. But what about the rest of the sea? That's where a technology I developed at NASA called MIDAR comes in. And MIDAR works a bit like a radar or LiDAR in that it brings a light source with it. We use narrowband hyperspectral emitters, usually very efficient laser sources or LED sources, and we've walked through the entire electromagnetic spectrum that are relevant to us to find wavelengths that penetrate very deep in water. And what's exciting about MIDAR is with a couple of new NASA grants, we are building ultraviolet versions of MIDAR that can see very deep in the water column and also are relevant for marine systems that exhibit properties in the ultraviolet and blue because, unsurprisingly, they've evolved pigments in those colors, having that be the light that penetrates the deepest. So with MIDAR, when we take a picture of a coral like this, hopefully you can see in the bottom right, on top of that coral, there's actually a coral disease that's only identifiable in the ultraviolet band. And we're using the same technology to look at marine plastics from aircraft, as well as cetaceans and coral mapping. We just produced a new MIDAR instrument, which I shared in the marine debris section, is looking at plastics, but works equally well for corals. And next up on the horizon, through a partnership with National Geographic, we're further integrating these sensors onto electric hydrofoiling flying boats. So these are essentially aircraft that fly on the sea. And on them, they have fluid lensing sensors, so we can fly our gliders in these remote locations. They're decarbonizing a lot of the marine research, which is very important to me, as we don't want to contribute to the very problem that's killing off corals, which are one of my favorite organisms. And on the bow of this, we have a very high power MIDAR array that's tied into the vessel, so we can not only image the benthic surface on this vessel, but not disturb the surface while we're doing so. So it provides a really good test bed for airborne platforms before we go out and do a large airborne campaign. So if you're ever in Miami, come out for a flight on this vessel. It's arriving this summer. It's tremendously fun, and it's a bit guilt-free. If you'd like to learn more about these technologies, I encourage you to check out not just this special issue in oceanography, but all of the other oceans across the solar system's efforts. It's really quite fascinating, the technologies that are being developed on our home world that'll hopefully fly to space one day. So thank you very much for your time.
Right. Thank you so much, Vade. So I hope that was a good warm-up for everybody. I'm pleased to introduce our next speaker, Dave Schimmel, who's going to talk to us about the global carbon cycle in the post-Paris era. And I just want to tell you that while Dave makes his way up here, in my copious spare time, I dug out of my files this morning the carbon cycle, ecosystems and biogeochemistry roadmap from NASA from 2003. And we had on there that one of our biggest goals is to quantify the global carbon cycle. So Dave is going to talk to us a little bit about if we've done that.
So every 10 years, NASA takes stock and develops a roadmap for the next 10 years of missions, kicking off a long process of formulation. And formulation at NASA is an art and a science that starts really with trying to identify the background, the challenges, and the motivations. And our dirty little secret, sometimes we start out with a really cool technology that we're looking for an excuse to use. So I'll be non-hypocritical about that. JPL is initiating its own navel gazing about the next decadal survey and really the future of NASA's observing and science program, thinking about what the world will be like for missions that launch around 2035 and will observe the world through to, let's say, about 2050 if our mission lifetimes are anything like they have been in the past. I mean, hopefully they'll actually be longer, not shorter. And I'd like to reflect, we've heard a lot about EOS from the Legends team yesterday. The amount of work, forward thinking, modeling, imagining the world, imagining climate change that went into EOS, which is now sort of hidden, forgotten, or buried. That's why MODIS is such an incredible program, because an enormous, enormous amount of forward-looking work went into it. And the way you can tell that it succeeded is because all of that work is now invisible. It succeeded in producing the right instrument for the time, and that's the sort of invisible success that we're hoping for with the next decadal survey. Do I just push this top button? So we've been studying the carbon cycle for a while. This is my first carbon cycle budget figure from the 1994 IPCC special report on radiative forcing. And we've been making figures like this ever since. And the point that I want to make is these figures all look about the same. They have a box for the atmosphere. They describe the ocean in varying levels of detail. They have trees and factories. But they're really not the same. There have been tremendous changes to the carbon cycle. And we're entering a period where carbon cycle climate feedbacks and perturbations to the carbon cycle are not just a fascinating subject and a really good way to get into one of the high-profile journals. They're something that are affecting our daily lives and our systems. So we're looking now at policies that are built around these sort of notional climate change scenarios. And I only include the 1995 figure on the left to poignantly remind us how much easier it would have been if we'd tried to turn the corner 25 years ago in Kyoto, rather than waiting until the last brinksmanship moment, which is what we're doing now. But I want to make another point, that if we do succeed in mitigating according to the most to intermediate ambitious plans, that is the lower scenarios that stabilize at between 1.5 and 2.5 degrees above pre-industrial, we will be at peak radiative forcing and peak temperature during the next decadal survey, right? So the world that we're building our next set of missions for is the world that we've been anticipating with global climate models for the past 40 years. It is the world when global warming will peak. Presumably that will trigger a whole series of knock-on effects that even if we stabilize radiative forcing of climate, it's likely that ecosystems, the cryosphere, and certainly the oceans will continue to change for many decades after that. And that is the world we will be trying to provide observational decision support for. And that's a really different framing. It may not change the instruments or the observations we propose, but it may fundamentally change them. And we have a couple years before the decadal survey to think about whether that world, instead of living in the eternal now, to think about whether that world motivates a different program. And in fact, at 1.5 to 2.5 degrees, even though there are a number of articles and very thoughtful perspectives that have argued that 1.5 to 2 degrees is a safe operating space for humanity, in fact, we know now just from living through wildfires, hurricanes, derechos, coastal flooding, we know that it's not a soft landing, right? We had a number of really super experienced industry and defense scenario planners meeting with us at JPL, and they said, well, we're kind of assuming that if we coast into a Paris Agreement world, we're okay. And we said, well, we're okay, but we have a very complicated, very challenging, very demanding environmental management problem. We're going to have at least as many, if not more, extremes as we do today. We're going to see continued change in the oceans from acidification and temperature, ice sheet melt, and presumably will be triggering long-term changes to terrestrial ecosystems. So in fact, many of these tipping points are likely to tip as we move into the stabilizing world, if they have not tipped already. So from the point of view of the carbon cycle, I just want to focus in on my own area. We tried to think about, and in particular, given that there's a tremendous amount of ferment around greenhouse gas information, climate change information in the US government right now, what is it that we really need to know about the carbon cycle? Well, thinking back, first, we need to know what scenario we're actually achieving. That requires understanding how much greenhouse gas burden is being added to the atmosphere. It requires quantifying emissions from anthropogenic activity directly, from land use, land cover change, from the whole NASA program. But the Earth system takes those concentrations and reacts with them, absorbs them, biologically processes them. So there's not a one-to-one relationship, and our models do not show a one-to-one relationship between emissions and concentrations. So we also need to know for any given scenario what radiative forcing and what climate scenario, what temperature and associated climate scenario that emission profile actually leads to. And I just want to use two of the icons of the carbon cycle to remind us how much things are going to change. On the left, my colleague and I took the healing curve and we detrended it, and then we wrapped it back around three of the scenarios that stabilize. And that's what we should be looking at if we are able to achieve stabilization. In fact, there's enormous uncertainty around exactly where those wiggly red, green, and blue lines are going to wind up because we don't know the airborne fraction. We don't know the extent to which land and ocean uptake will change, nor do we know where. So looking at the inner hemispheric gradient that reflects the balance between fossil emissions and land and ocean uptake, where are the big changes going to take place? They're going to make this profile look, we hope, very different from the way it's looked over the observational era. And we have good reason to believe that terrestrial ecosystems and the oceans will be very close to sensitive points. This is from a paper by Catherine Duffy, where she argued by developing temperature relationships for photosynthesis and respiration from the global eddy covariance network that we're in fact very close to much of the world shifting from being, just in terms of physiology, being a net sink to being a net source as the exponential dependence of respiration takes over from the optimal relationship that photosynthesis has with temperature. And that's before you load drought on top of it. And just to the right, a figure that Pierce Sellers and I published when giant tigers and mastodons still probably roamed the Great Plains, showing a result very similar to that from a simulation model. It's in a paper that was part of the observing system simulation basis for the EOS observatory. For the Amazon, which is a kind of a burning postal child, there are several recent papers that have shown through, this is a dynamical systems approach looking at the time series, autocovariance, critical slowing, that the Amazon, many regions within the Amazon are approaching a tipping point. This is work from Luciana Gatti and others showing that, in fact, over the past decade, as a result of drought and land use change, the Amazon may have already, in fact, transitioned from being a net sink to being a net source. These are the kinds of changes that we should anticipate accelerating over the next decade, and which should be sort of in full bloom, so to speak, during the next decadal survey era. So we're going to be looking at life on a rapidly changing planet. And I want to graphically illustrate these two challenges for the carbon cycle. We need, in order to understand whether we're on a stabilizing emission trajectory or not, are entities, countries, firms, and citizens meeting their commitments to stabilize their emissions. We need to monitor emissions, because it's only by monitoring emissions we can know whether we're on a low, intermediate, or high trajectory. Right now, we're still on a very high trajectory with a few optimistic signs. So monitoring emissions can help us figure out which of the scenario worlds, which future we're headed for. And that leads to immediately actionable information. We can say, there's a giant methane leak in, just to pick a random example, Turkmenistan, let's go fix it. Deforestation is picking up and there are sources in the central Amazon. Let's work on policies to inhibit them. But they don't in and of themselves tell us what climate we're headed for, because the uncertainty around each of those emission trajectories, because of uncertainty about what the ocean and the biosphere will do, is very, very high. And it's only by monitoring fluxes and concentrations, processes, feedbacks with the water cycle, all of the things that influence the way the ocean and the land work, that we can understand what climate we're going to get with the scenario that we appear to be on. And it is that scientific uncertainty that informs our planning for resilience, that might inform our understanding of vulnerability, and which might motivate additional mitigation to get down to an even lower scenario, because these scenarios overlap. We might actually have to go to a lower emission trajectory if the Earth system feedbacks aren't helping us out as much. And so we can really think about our understanding of the global carbon cycle in the Earth system as a function of the forcing from emissions, the feedbacks, and the resulting concentrations and radiative forcing. So, observing strategies. The world will be very different from now although we might think of it as being just ever so much more so. Extremes, tipping points, sea level, like now, rapid changes, but even more so. It's almost certain that the trends towards changes in extremes will continue. Carbon cycle thresholds, regional ones at least, are likely to be crossed. Wildfire is certainly going to play a major role as drought increases with warming temperatures and changes to the water cycle. Early warning signs may come from dynamic behavior, time series behavior, as in the first Amazon paper that I showed you, or they may come from better understanding of fluxes, processes, and dynamics. We need to be able to lean on the long record to be able to understand the baseline that we're moving away from. But those measurements may not be a complete guide to the processes and dynamics that we're going to see in the next era. And we need to think carefully about that. But I really want to emphasize, they may be a perfectly adequate guide. They may not be a perfectly adequate guide, but we need to ask that question as we begin to go into formulation, rather than making hidden assumptions about how the world might work. So there's this great quote from Winston Churchill that I first heard from Pierre Sellers, that says, gentlemen, we have run out of money, now we must think. And that's really where we are now. And we've heard from our leadership and our program teams that we kind of have run out of money. We're working with very tight budgets, and a lot is expected from us. And so we need to not just keep on doing what we're doing, but we need to think very carefully about what we should be doing. We need to be thinking about observing emissions, concentrations, and fluxes on the carbon cycle side. We need to be thinking about key controls that might give us a little bit more predictive insight into what's happening. But we should focus those process studies on things we genuinely believe might give us insight into the futures. We need to be looking for critical tipping points, early warning signs of them, and ways to mitigate them, perhaps head off the most rapid and abrupt changes. And all of this kind of thinking, this scenario thinking, should inform much, much more directly the planning, the white papers, and the execution of the next decadal survey, so that with finite resources, we're able to build a critical resource for supporting environmental decision-making and serious political debate in a rapidly changing, really quite warm world, which might be a safe operating space, but as I said, it does not look like a soft landing. It will be a very challenging world, and the remote sensing and Earth system scientists of the next generation are going to have a big task. We need to make sure that we equip them with the right tools. Thank you.
Thank you. Thank you very much, Dave. That was very insightful. I mean, there's no question NASA is among the only agencies that provides a wide angle view of our Earth from space, right? And so the inspiration to not only think about the application of our data, but that purely discovery-driven research, especially with something like our carbon cycle, is really critical. All right, with that, our next speaker is Chris Justice from the University of Maryland. Just walked across the street to get here. No, I'm just kidding. Climate impacts, mitigation, and adaptation through the lens of land use. Take it away.
Thanks, Paula. Good to see you again. It's got a late in the afternoon, and I was asked by Derek to talk about future research through the lens of Vancouver land use change. And that's exactly what I'm going to try and do. I would say that the research that we're doing now is likely to continue in the near future. And so go and look at the posters. That's what we're likely to see more of. But we need to be looking in the longer term, as Dave was mentioning. So I'll try and operate this. We've seen this slide a number of times. And I just want to say that this is the current structure, right? This is where we are in terms of the focus areas. And for us, we're supposed to be talking across the programs that are within this circle of carbon cycle, ecosystems, land use change, biodiversity. And there's a missing stovepipe from the program that needs to be shown, which is we rely on the Earth Sciences data system to get the data that we need to do our science and to share that data and make it more broadly available. So how do we get here? You know, I can also give a little bit of history. I could also give some Piers Sellers quotes, but I think particularly referring to Dave, but I won't do that because I want to be really collegial and talk about this diagram, which those of you who are a little bit long in the tooth will know this very, very well. This is the Bredesen diagram. This was designed to justify Earth system science and EOS, Mission Planet Earth, in the 1980s. And if you look at this, and I show this to my students, if you were going to design a digital twin of the Earth system, you would have to have modules in each of these boxes. But this was great, and it really set the sort of the flavor for what we did with EOS. And the data sets that we generated and the products that came out of that were to feed the models that could then be used to get the forecasts and the projections of climate that Dave's talking about, the climate models, but also the process models that we heard about there, carbon cycle modeling. What I want you to do is to look at these two areas here. This is basically where we sit now, our ecosystems, carbon cycle science. But look at the size of the box for climate change in the 1980s, and look at the size of the land use box and the CO2 box. I would posit that if we were going to redesign this diagram for the current era, we would have those much more central because human activities now are really dominating the system. We don't want to stop understanding that physical climate system. We don't want to stop understanding the biogeochemical systems. You heard that from Dave just now. But we really need to move this more central. And I would say that this is probably the centerpiece of what the current diagram would look like, where you've got climate change, you then have land use and the relationship between land use and climate change. And I would say that I was really interested to hear Scott Getz's talk about terrestrial ecosystem, but the question is, what can we do about those changes that we're understanding? With land use, we have an opportunity. Human response to climate change is that we're going to mitigate. Okay, and that includes the MRV talk that Dave gave this morning on carbon cycle, yesterday, sorry. And then the human response, land use adaptation is all about resilience. And I would say that if we're not careful, we've got to watch the climate change agenda, because if there is another swing, we could have people who say that climate change is not important and anything that's in the NASA budget on climate change can be written out. That has happened before, not to NASA, it happened to NOAA directly. But I think resilience and land use resilience to extreme weather and climate change is something that everybody can get behind, regardless of which side of the aisle you sit. So I would say that this is an important area for topic, and I'm going to talk a little bit about what we're doing in the future research for land use change. So the pressure, as we've heard from several presentations, on land is increasing. And some very large areas are changing rapidly. And that was Matt Hansen's talk, which I think really set the stage. And then how people use the land is inherently societally relevant. And I think that's something that the senior management headquarters is looking for, is how is our work relevant to society? We're not NSF, we're NASA. To understand land use change requires understanding human behavior and the human dimension. We used to call it human dimension, but the social science is an underpinning there. And that was Karen Sito's talk that you saw. I would say, though, that if we wanted to forecast human behavior, it's a real challenge. So the models, land use models, are really in their infancy, but you have to understand that if we're going to do scenarios of change and we want the humans in that mix, we've got to be a lot smarter, and that's a research priority going forward. So land use can be changed to be more resilient and to mitigate climate change in principle. We've had huge problems in this country making sure that that happens. I think you have to have an economically viable approach so people see the benefit and the cost of participating in that. But I think for resilience, we can see that with California wildfire. There's a lot of enthusiasm, a lot of money now being poured into how do we make society more resilient to these extreme events. So for me, land use change science provides a foundation for developing what everyone is sort of talking about and getting nervous about, which is developing the relevant information for land management decisions. And I think Krishna pointed to some of the complexity of that this morning, and Dave's talk also. So in our science team meeting last week, we had some topics that we went through. These you can read through. There's a lot of interest to do a lot of stuff, far more than we can possibly afford. But we're likely to see some effort on integration of finer scale land cover in next generation modeling, sort of a trip sort of back from the past where we were trying to use ISLSCIP, which was the land surface climatology. We're trying to get that work done so we could parameterize our models better. We're going to see some work on a digital twin for land use. And we also need to continue this looking at the socioeconomic impacts of land use change, because I think ultimately that's the important part that society is concerned about. So we have a number of challenges. This is a program presentation. The science presentations are outside. We have a limited temporal availability and access to very high resolution data. Everyone's thinking that we can do so much more, and certainly it's a game changer for land use science. But we need to have the budget for large volume processing, the difficulty of integration of data from inside and outside the cloud. There are a lot of details. These came from our meeting of what the scientists are dealing with now. I would say that most of these challenges can be solved by increased funding, no surprise. Doing the same and asking for more on the same amount of money that we've always had, at best, is a short-term solution. We need a big game change. And I was going to ask that question, but early career scientists moved to the front of the line. My question was, what is the plan to get the budget back up to the EOS level where after huge cuts, we were at 8 billion, and now we're around 2 point something. To do the science that needs to be done and to meet the charge that Dave just gave us and everybody else, we need a bigger budget. That has to come from the community supporting our management to do that and making the case for it. So let's talk a little bit about missions, and Paul is going to keep me on time. Trouble with being an academic is you can talk at length on anything for any amount of time. Missions. So the future research will require well-calibrated measurements from space. Let's not forget that. This is what Dave was talking about in EOS missions. We need to emphasize this when we come to senior reviews, decadal surveys. You're not on those now, or you might be. You will be in the future. So we need to keep this in mind. Science requires accurate measurement. With a small number of missions, and I would say I'm very happy to see the fleet diagrams, but for the land community, we've got 3 missions. We might have Return of the Jedi. We might have NISA. Hopefully we'll get Landsat next, the 3-day super spectral cycle, and then a SPG will come. Whether I'm still here or not for SPG, I don't know. And Dave, maybe, I don't know. But this is going to be a while, and we've got to watch the budgets. Very high resolution data opening up new avenues. We need to move from evaluating these commercial products to extensive use of them and the associated computing capacity to do that. I suggest we need a partnership with the emerging commercial EO ecosystem rather than just we'll buy your data and give it to our scientists. Okay, that true partnership needs to come. And I would say that future research for NASA, once everybody gets over this angst about private sector competition with the federal government, we would benefit from a high resolution public good satellite with the associated NASA quality data systems and delivery systems. So on data products, you can read this too, but I was just going to make the same point. The data systems that NASA has developed a huge reputation internationally. We heard about some of that this morning. And I would say we have an opportunity to continue that reputation, developing new approaches, right? This is what Dave was saying. It's not the same old. New approaches to analyzing new missions, and NASA in the cloud is in development. And then the future research to develop how we get better access to those data. And then the need for well-established NASA process that we've got for data product generation, which I think is going out the window and we need to be very careful about. This is peer-reviewed algorithms, quality assurance, accuracy assessment, validation. Okay, I'm not hearing those words when I'm hearing about new data sets coming out to meet the Science Needs Working Group. Perhaps I'm just not seeing the right overhead presentations. But I think at the moment, we've really got to think about this. And we need some archive, cloud-based production, reprocessing, and access. And you heard that question from one of the early career scientists about that. International collaboration, we have a global reach. I know there's a lot of focus on the US. There's a lot of focus on trying to get our constituents, happy and promoting NASA. But there is a global program. And I think what we heard is that there are impacts of climate change are unequal around the world. And we really need to be able to think about the global community and where those big changes are taking place. We launched our Southeast Asia Research Initiative for that reason. The LC Luck program did SARI. The research program will continue to foster partnerships with Global Land Project. Ariane de Bremond is now bringing that to the University of Maryland. I'm not particularly promoting University of Maryland. I'm just saying in the US now we have a chance to help promote the Global Land Project, which I think is really important way of bringing together scientists that do land use. And then we have our global regional networks of scientists that really know what's happening in the regions that we engage through our GovSeaGoal regional networks. 1 minute. Okay, looking ahead. So this is my sort of summary, but basically what I'm saying is whether we're managing impacts of extreme weather on agriculture, heat waves on urban communities, fires at the WUI, mitigating emissions from AFOLU, or implementing sustainable water management, climate resilient agricultural practices, the future research will provide the scientific underpinning. Let's not forget that the science is required before the applications can happen, and respond then to the management challenges associated with climate change and economic development leading to societal benefit. Thank you.
Thank you, Chris, very much for that. Okay, our next speaker is Francisco Chavez. On my way here on the plane, I read this article that said 42% of the world's population gets at least one protein source from the ocean. And that's expected to grow tremendously. And I know our next speaker has been spending a lot of time in his career thinking about those protein sources. So talking to us about observing and modeling life in the sea, present status, and a view towards the future.
Thank you, Paula. Now, this will be a little different talk from the ones that you have been listening to. Originally, Heidi Sosik and I were going to share the podium, but she couldn't make it. So I'm presenting for both of us, although most of the material comes from me, but I left Heidi in. So you shouldn't blame her, blame me if you disagree with any of that. Anyway, the vision that I want to bring forth is that we need accurate and comprehensive biological assessments of marine environments on a global scale, which we don't have today. It's kind of embarrassing that we know very little about life in the sea. And we've made huge investments, NASA has been among them, into globally deployed physical and biogeochemical systems, but there are no really equivalent technologies for conducting biological assessments at the time and space scales that we need. So the goal of those people that develop technologies for observing the life in the sea is to increase our ability to observe and quantify how life in the ocean is changing over space and time. I'll speak very briefly about models, only to say that they're important for a variety of reasons. One is they test our ability of how well we understand the ocean. We can use them to fill in our low resolution measurements back in time, and we can forecast the future. However, forecasting the future isn't easy because most of our models are developed for things that we know are happening today. And many of those things are changing, as many of our speakers before have intimated. Today, we have this unusually warm water off the coast of Peru that looks like an El Nino, but isn't one. There's decoupling between what the California current is doing relative to the Peru current. So things that we hadn't seen before are coming around. So anyway, our predictions of the future will necessarily be imperfect. And then the last point, the important point here, is that models, the fidelity and accuracy of our models are directly related to the quantity of observations that we have for the properties that we're trying to model. Hence, of course, they're better for physics and biogeochemistry is catching up. but they're presently pretty weak for biology. So our traditional approach to monitoring biology in the ocean is to go out to sea on a ship, collect samples, use nets, water samples, process the samples visually a lot of times, and then takes us years to synthesize that information. We have a new set of requirements today because of what the previous speakers have already been talking about. The world is changing. We need real-time information, which requires continuous presence. We need the information to be globally distributed because things in the ocean move around a lot. When a fish stock disappears, did it move somewhere? We have no idea. We need it to be multidisciplinary. We need to go all across the food webs, and we need it in real time. And most of the technology that I'm going to talk to you today is about environmental eDNA. But I do have a slide from Heidi, and there are other evolving technologies for measuring life in the sea, and Heidi has pioneered one of them. And she now is able to make measurements over kind of the right time and space scales to evaluate how they do relative to remote sensing. And there's a growing toolkit of imaging and acoustic sensors. But today, as I said, I'm mainly going to talk about environmental DNA, and I don't know how many of you know about this, but basically the techniques were pioneered by people studying microbial populations in the ocean. But it wasn't until maybe a decade or two ago that we discovered that everything sheds. And of course, we know that from forensic science. If there was a crime in this room, the forensic scientists would come in and comb the room to find residues of and see if they can find the suspect. Well, our suspects are life in the sea, and animals and all kinds of other organisms leave behind a residue that we can pick up. And then we can use different methods to target different types of organisms. And typically in work that we're doing as part of the Marine Biodiversity Observation Network projects, we're targeting 4 different markers that range from vertebrates all the way to microbes. We can target single species directly, or we can target groups of them. And with those data, we now can make profiles of life in the sea that look surprisingly similar to what we would expect them to be like. And on the left side, I'm going from diatoms to copepods to several species of fish. And these profiles look pretty much what we thought they should look like, with maximums for some of them at the surface, and those that live deeper, like the hake and myctophis, found with maximums below the sea. So we have the potential to make maps of the ocean for life in the sea, like we do for temperature and salinity today, perhaps. And we've been able to go back in time for samples that we had collected for other reasons, and showed that we can see changes in these communities associated with the regime shifts that we're all familiar with. A big driver in the Pacific today is the North Pacific Gyre Oscillation, and these 3 series, one for vertebrates, one for invertebrates, mostly zooplankton, and one for mostly phytoplankton, seem to change at about exactly the same time associated with these changes in the MPGO. In a way, this is a little surprising because we might expect lags between the different food groups. But then now I want to talk to you a little bit about work that we're doing at MBARI in collaboration with Johns Hopkins, which is not too far from here, to automate the processing of eDNA samples. And this is the basic workflow. You collect it, you concentrate it, you extract it, you prepare it, you sequence it, and you run some bioinformatics. There are now systems that can go on remotely operated autonomous vehicles, and perhaps someday on floats like those out for Argo, that could perhaps collect the sample, process it, and do it all in situ because of new developments in sample collection, microfluidics, miniature sequencing, and high performance calculations in small packages. Just to talk a little bit about some things that came out of a second National eDNA workshop last year. The conclusions are that the science for eDNA is beyond does it work. It's been demonstrated in biodiversity surveys, it's survived litigation, and there's a whole slew of new things to do. And there is a national eDNA strategy being developed that hopefully involves something like a satellite mission in terms of eDNA. So in summary, observations of ocean physics currently provide important near real-time information of large-scale climate, state, and local conditions. We all use those routinely. Observations for biogeochemical properties are improving and in a decade or so may rival those for ocean physics. Ocean observations of life in the sea are woefully behind, not because of the lack of effort. People really work hard going out on these surveys and towing their nets and counting the fish that are in there. They really work really hard, but we're hampered because of the lack of adequate sensing systems. As a result, ecosystem information is normally not available at the right time, slow and outdated and sparse scales for effective management of life in the sea. The lack of adequate data hampers our models, and we argue that timely and spatially distributed biological data will improve management of our marine resources dramatically. And I'd like to finish with this slide that just, I kind of put this in the satellite mission parlance, where I think we need NASA-type engineering to develop a system for observation of life in the sea that would manage all of this, because eDNA data, I think, is quantitatively, qualitatively similar to that we collect by remote sensing. Thank you.
All right. Thank you, Francisco. So the final speaker in our session before we invite everybody up for a panel discussion is Danielle Wood from the Massachusetts Institute of Technology, who's going to pull it all together for us and talk about using Earth observations when assessing environmental, social policy, and technical factors to support sustainable development.
Thank you, Paula. All right, everyone. Last talk of the day. Are you with me? I need a little help. So before I get started, oh, I like that. I like that. It's a good audience. This is why I love coming to meet you all at these meetings. Before I start, I want to make sure you're all awake as I hear the good energy. So stand up for me if you consider yourself primarily a fundamental scientist in your work. So you see some standing. I need some energy. Stand. Stand up. All of your chair. All right. Thank you there. Remain standing if you like, or stand up if you also consider yourself someone who does applied sciences. So if you want to do both, that's also great. All right, we got most people in the room. All right, now sit down unless, or raise yourself if you are also active in social science. So sit down if you're not in social science, but stand up if you consider yourself a social scientist or working hard on social science. Got a few folks. Good to see you. Good to see you. All right, you're welcome. All right, wonderful. Thank you so much for joining me. I wanted to get the energy flowing in the room, so glad to be with you. And I think I want to highlight that I hope in future joint science workshops, we have even more of those who are on the social science here with us in the room. I myself am cross-trained in engineering, professional training in applied sciences, and a lot of my students and collaborators come in social science. And I think we need all of these tools to go forward. I'm here to ask questions around what it means for us to use our science and applied science results to help meet the grand challenges of our time. Right now, the global definition of our grand challenge as a global community is often summarized with the Sustainable Development Goals. How many of you are familiar with these? Hopefully, all the hands go up. I see a lot of hands. Now, it's 2023. That means we only have a few years left on this version of a global mandate for societal development. It means that we are already thinking about the next future versions, and the post-2030 world is just right around the corner. So, of course, this is a hard challenge, but the next definition of the harder challenges are continuing. I appreciate the comments earlier. So we want to ask the question, how is our work contributing not just to the excellent results and publications and insights that we bring, but also to the question of how people who are not in the room use our results to help bring about these kinds of outcomes, eliminating extreme poverty, ensuring there's access to food, clean water, and healthy oceans and biodiversity on land. We need additional skill sets beyond those that are often in the room, and we need to become good collaborators with people in policy, social science, as well as different forms of management. One of the reasons my team exists at MIT, I lead a team called Space Enabled, and we're often collaborating with other teams, especially at NASA Goddard, East Carolina University, and beyond. We're often asking, why is it so difficult to take results from Earth science applications as well as scientific results and use it in policymaking or direct societal applications? I want to give appreciation to Dr. Raha Hakimdavar, who's here in the audience. Hi, Raha. Thanks so much for getting us published in one of our results. A couple of years ago, we had a workshop hosted by Goddard and bringing together organizations, especially from the government communities. We had several military organizations at the State Department, and we spent a whole day asking how we can use satellite data for transboundary water management. But in the process, we also made this picture to highlight all the steps that normally have to happen to move from having observations that we believe and we are validated and calibrated into eventually being useful for societal responses. And it's a lot of steps, especially in the color schemes you see. The public sector funds are often focusing on steps 1 to 5, and there may be private entities collaborating with the government, especially on steps 6, 7, and 8. Steps 6, 7, and 8 often require very interdisciplinary teams that must work together across physical science, as well as social science, as well as data science or different forms of artificial intelligence and understanding user interfaces on the software side, and eventually making good designs to present information, usually through maps or other forms of interactions. It's a lot of work. And I don't see an easy way to make it less work anytime soon. Sometimes I talk to friends in computer science, they say, well, just take all your data and put it into a wonderful AI, it'll be fine. But we know better that we want to be careful to continue to preserve our understanding of the science nuances while also using the latest data science tools. And ultimately, this is about humans coming together and sharing our different skill sets. So one of my calls to action for our community is to say, let's continue to consider the human element, both in the outcomes we're trying to achieve and also in the teams we're trying to build. In my team, my core training is actually in system engineering. We also bring together a series of processes. I want to make a proposal that even though we often talk about what it means to engage with stakeholders and to make sure we're having listening sessions, even more rigor can be done with that. My team uses a systems architecture framework as just one example of a design framework that works for this. I want to appreciate Severe also. They have their service planning toolkit. You can definitely reference that. But please, when you're planning to do stakeholder engagement, don't just have meetings that you plan off the top of your head. Go to some rigorous techniques that are known and demonstrated to be useful for collecting the kind of information that's needed. And I want to put out a call to say that it would be useful also for solicitations to require some form of rigorous technique for stakeholder engagement, because there's many published already. In my team, we start by asking what the context of the systems are, who stakeholders are, both those who have decision-making power and those who are what we call tertiary stakeholders, those who have less power but are the beneficiaries, or those who are sometimes victims of the results of the system. We think about the objectives, the functions that are going to be proposed by the systems we're building, and eventually we compare alternative forms of building them and how to monitor them. This leads to then a question that says, how can we make an information system that can help answer questions for policymakers, usually at the regional or urban scale, or sometimes national scale, who are working toward one of the Sustainable Development Goals. And I want to give a few examples of the ways that these projects are carried out in real life, but also highlight that this kind of thinking is needed to take our results into action. And it has 4 key things I think we don't always do together as a community. I think we're very strong in this room. In the first section, we call the E model. We ask the question, what's changing in the environment? How strong is our confidence? What's our accuracy of that environmental analysis? And we can make maps showing patterns. That's wonderful. Then we want to ask how humans are impacted by that change. So the next is a series of different maps, often created by economists, sociologists, and other geographers. And we're trying to overlay the environmental change with the social and human changes. Then we want to ask either, what have policymakers decided, or what are the options laying out to them? And another question we can ask simultaneously is, which technologies are we currently using for environmental observations? And should we be redesigning them? I just want to give appreciation. I think in the weather community, they have a really strong tradition of the OSSI, the Observing System Simulation Experiment, where they regularly ask, if we added a new sensor to our process of doing the daily forecast, what would be the increase in accuracy of the environment? I think we should all find ways to do different forms of OSSI-like work in our work. It's a lot of effort, and it's very expensive proposition in the weather community. But there's probably lower scale ways we can do it for smaller questions, just saying, let's simulate a design for a new sensor, such as adding drone data in addition to satellite data for a certain question we're asking, and try to see how much benefit we get from new technology investment and compare whether it's ground-based, air-based, and space-based data sets. So we put all this together, we call it EVDT in my team. I'm very excited to say that the PhD student who is first published on this is graduating in a few weeks. This is Jack Reed, I want to appreciate that. So we're having the first of a series of PhDs in my team using this kind of framework. And we're taking them all over the world. So we have projects right now actively using this framework in California with the Yurok tribe. Thank you for the land acknowledgement. I want to also acknowledge that I live and work on the land of the Wampanoag people. And I've just met my first collaborator from that community, so I'm very happy to start to get to know them. But the Yurok tribe in Northern California invited us to work with them. And we've now had another PhD student use this EVDT to ask how they are monitoring their ancestral forests, especially from the point of view of preserving forests that lead to carbon management. Also, the city of Rio de Janeiro has worked with us for several years. They're asking how they monitor their mangrove trees, but using the same framework. In Indonesia, they're concerned with coastal resilience, in this case also seeking to use mangroves to support communities affected by flooding. In Angola, thanks to the Water Resources Program, we're focusing on how to address drought by using SMAP data to monitor drought. But what I want to emphasize is in all these different localities, we're asking these same 4 questions. What's happening in the environment? What are the social and economic impacts? As well as what's happening from the point of view of the policy options that are there, and then what technologies could be added or changed for the sensing. So all these examples just lead to a few key recommendations. I'll just note the rest of the slides are posted online. There's examples coming from Ghana and from Benin, from our work on even applying the same framework to COVID. I'll leave that for you to scan another day. But I want to give a few key findings because we've tried this kind of appreciation of combining social science with earth science alongside policy analysis and engineering in multiple places around the world. So here are our lessons. I started by asking what makes it hard to apply our powerful data for the SDGs or other development goals. One of the reasons it's hard is that we actually have not yet identified the skill set that we're celebrating. I also serve on the advisory council, the PACA committee for the earth science here at NASA. And we identified the fact that as young professionals are coming into grad school, they may be tracked, for example, in science or in a certain subset of science or social science or geography. But what if we identified the professional skills needed for the applied scientist? It's really a blend of several things. It probably includes some skills in 1 or 2 of the core science areas where they get to know the exact nuances of that particular sensor type and that family of data. They also need to then be familiar with what it means to apply design thinking and spend time engaging with stakeholders. They might need experience in addressing policy categories and seeing how that can be changed with the kind of data you get. And ultimately have some familiarity with computer science, artificial intelligence, machine learning, and even some user interface design. So I've been training students that work through all these series of training alongside really many mentors. And it's a lot to learn, but a student who's had exposure to all these things can really be an applied science professional. They can help to make a bridge between the excellent science results we have and those who are charged with responsibility to use that data. So one hope I have is that our community will start to name this as a professional goal for young professionals to move to that direction and then give appreciation when they combine these different skill sets. Number 2, of course, we need to continue to build teams. It may be that one person may not actually hold all those skills in depth. We need to build teams that represent all these organizations so that next time we get together for joint science workshops, our economists, collaborators, sociologists, collaborators, and geographers are in the room with us. We need to use systems-oriented approaches so that we are considering not just the physical environment, but a broad understanding of the social and cultural environment. And that includes listening, especially with humility, to indigenous communities which are really linked to every part of the land all around the world, who have a long-held understanding of the environment based on their generational knowledge. And the final piece that our team is also thinking about is making information technology work for us. So I mentioned these 4 different projects. There's several more examples in the slides. So we hope in the future to combine the software that we're developing from all these codes into a family. For now, it's on GitHub. It's the beginning of a library. But we need libraries of reusable code that are adaptable to new situations. We've learned so far that our mangrove code in Brazil and our mangrove code in Indonesia aren't exactly the same, but they certainly are related. And we want to be able to make it easy for new teams to come in. I want to just give appreciation that and with funding from the teams here, especially from ecological conservation, we've been working for the last few years in Benin and Ghana, and there certainly are close collaborations with scientists in each country, and they do love to use the data and they know how to use it. There are barriers in terms of funding and cost, but it's not because they're not ready to use, they are. And so we as the American guests in their country are often there mainly focusing on how to convene and bring together the right teams to make it possible. So I think when we bring respect to these local collaborators, we can work together very closely, and these are very fruitful collaborations. So with that, I will pause and look forward to conversation with all of you. Thank you so much.
Thank you, Danielle. I'd like to invite the speakers in the session up to the podium so we can have a bit of discussion. And I think if you've got any questions, feel free to step up to the microphone. If not, I'm happy to start. I always have questions. Anyone? I see motion. I'm not sure which way it's going. Okay, yeah. Who's ever ready? I don't know who got there first.
Okay, I'm Ryan Pavlik at JPL. This is mostly to Dave and Chris Justice. You both mentioned, looking at future missions. Chris, you mentioned, the tension between public and private space. And Dave, you mentioned looking at what is the world going to be like in 2050. And Dave, I was wondering if you thought at all about geoengineering in the mix, particularly solar radiation management and how we would observe those sort of interventions in the climate system. And then for both Dave and Chris, I mean, thinking about the next couple of decadal surveys or even this decadal survey, commercial space is now moving at a really rapid clip. Just last week, the first commercial LiDAR mission was announced. I mean, whether it actually takes off, we'll see. But what do you think about that, and how are we going to contend with the pace at which NASA moves versus how fast industry moves?
So to the first question, in our sort of forward-looking, we've thought about both branches of geoengineering. So the first that we've thought about is geoengineering associated with the carbon cycle, which typically involves creating either engineered or biological, biophysical sinks. And I think that for most of that, the observing system design could be integrated with other observations. But if you imagine a world that's very warm and dry, but with lots of carbon capture and storage, you could imagine a world that instead of having regional sinks and point sources, had regional sources from climate feedbacks from the land and the ocean and point sinks. And I think that the observing requirements would be very, very different. So we've kind of played with that, and obviously we've also thought about the climate, water cycle, and radiation measurements that would be needed in a world that had either planned or rogue geoengineering going on in it. And I should say, I think, in the spirit of the recent Kim Stanley Robinson novel, I think it is important to think about the possibility that a technologically able but very climate battered country might decide on its own to try and fix its problem with solar radiation management. So that absolutely did play a role in our scenario framing, right? And we're not at this point proposing solutions, but I think it'd be unfortunate if the next decadal survey didn't at least imagine the possibility that there would be either centrally planned or rogue geoengineering, and certainly there will be some component of carbon cycle management going on. I mean, that is already spinning up.
Yeah, I'll take a go at the second question and the third question. So for me, the decadal survey came from outside of earth science into earth science, and we've adopted it. And I think Paula said earlier, it's just one of the inputs in which decisions should be made about instrumentation. One of my concerns is that the decadal survey is kind of contained by the budget that we've got. And I would say that what we need to do is step outside of that and talk about the budget that we really need first and make the case. So in the 1980s, three of the agency heads came together and they talked about System Z, which was the forerunner to EOS. And that translated then into 3 platforms with 11 different facility instruments. That was eventually pared down to what we had. But the vision was that we needed a satellite system construct to do Earth system science. And I think what we got was a really good system, and we need to do something similar now and create the budget and create the space for the growth. That growth cannot be for NASA alone. I think we've got to have a partnership with NOAA for the operational instruments. We've got to get that sorted in a way that doesn't mean that NASA also does what NOAA does, that we do what we're doing, and we work together with NOAA to try to get a combined effort. And we can talk about that in the context of JPSS and then the NOAA 20, NOAA 21. But we've also got to work with the private sector because the cost, if they go to the Congress and they say, we can do it for 1/10 of the price of NASA, or we can do as good a job, we've got to be there with the answer about the science quality observations that we need, but we need to think about working with them. If you look at the cost of Landsat Next, that's going to be $1 billion plus. And then you look at the cost of what they're launching hyperspectral and LiDAR instruments with. It's a very different system, but we've got to work with them. We cannot just let it go on, because I think what's going to happen is we'll be seen to be the dinosaur. And I think that's not what NASA is at all. So that's my input.
Yeah, George Hurt, University of Maryland. I wanted to ask a question maybe related to that first question, but press on it a little more. Thinking of the future 25 years out, presumably there will be large-scale climate mitigation efforts underway. And what I'm interested in is how important it's going to be to track the effectiveness of those per se. Because if there's large-scale investments in climate mitigation, it's going to be very important to society to monitor their investments in those efforts. And my feeling is that this is going to drive up the science requirements in general from what we're used to in just studying the carbon cycle. For example, in the case of Maryland per se, under state law, the state of Maryland is going to be net zero by 2045. It'll plant 5 million trees between now and then. That's on a background of more than 100 million trees in the state. And so we're going to have to monitor the performance of a kind of a relatively small signal against a large background, but this of incredible societal importance. And so I wonder what your thoughts are in that future outlook on how our science requirements themselves may go up due to the effort of climate mitigation.
By saying that when you look at the mitigated world, the 1.5 to 2.5 degree world, based on what we know about the carbon cycle, any ecosystem, tree planting, soil carbon manipulation, I think is going to be doing really well if it holds on to what we have now against the pressure from rising temperatures and drought and wildfire. And I think the idea that there's going to be significant mitigation through the biosphere based on what the science actually shows it's just a way of putting off the inevitable mitigation of emissions. So now that's just my personal opinion, but I think that position is very defensible from the science, and I think that the emphasis on natural climate solutions is an emphasis to avoid the really hard and controversial work of revamping the grid, changing from a fossil-based emission approach, and the idea that we could go from about 2.5 petagrams a year now to a world where with declining growth rates of CO2, we lose CO2 fertilization and retain a sink, it seems to me is really actually, we speak out of both sides of our mouth when we advocate for that as carbon scientists. The sink right now is driven mainly, and we heard many talks about this, is driven mainly by increases year on year of carbon dioxide. And when that goes away, the natural sink is going to shrink. The IPCC projects the 50% subsidy goes to a 25% subsidy as we go towards stabilization, and then it drops to zero. So we're trying to add substantial sinks to a rapidly declining terrestrial sink in the face of pressure that pushes everything in the opposite direction. So sure, if we want to delude ourselves that planting a couple 100,000 trees is meaningful relative to taking a couple million cars off the road, and we want to spend precious space assets on it, that's great. But I don't think it ought to be our honest priority. And the fact that policymakers want to delude ourselves isn't something that science should buy into. So I haven't spoken this directly about this, but I think it's nuts to think that the land is an important part of the solution in the future.
From what I understand, there will have to be active removal of CO2 from the atmosphere in some form or another. And the only place to store it is in the ocean. As you mentioned, I think the land won't be able to hold any of that. Anyway, I know there's a bunch of things spinning up in that space because of the fact that we won't be able to reach the Paris Agreement, even if, they're going to have to remove CO2 from the atmosphere in some form and store it in the ocean, is what I've heard.
Big thing that we need to do as we think about the world that Paris envisions, it's a rough place, but we can't talk about it in a way that makes people say, well, why bother? Let's just do business as usual. So I think it's important to be clear-eyed about the fact that the CO2 sink is largely driven by increasing CO2. And if we solve that problem, the sink is going to mostly go away. And that dynamic is built into every process model for the ocean and for the land. And that there are questions about the timescale, but that underlying dynamic is troubling. On the other hand, we don't want people to use that as an excuse for saying, woohoo, let's have a fossil fuel party.
Yeah, if I could add, just as someone who is part of a generation that grew up with climate anxiety, which is a kind of a first, I don't want to be too doom and gloom, because we got into this problem, largely, no offense, your generation got into this problem because of unintentional combustion, right, of fuel sources. And we now have, for the first time in human history, a global understanding of what went wrong and how we can correct it. And imagine what we can do if we just apply some intention to this problem, as opposed to living for a few decades unintentionally contributing to a problem. So for every tree that's planted, sure, the sink may be small, but the peoples whose minds are changed and the people who are asking, why is that tree being planted? What can I do differently beyond that tree being planted? That's going to be, I think, what leads us to a climate future.
I think the answer wasn't really my question. My question was that the humongous efforts in climate mitigation that are likely to come, that whether they be in tree planting or other aspects of the carbon cycle, the need to track those mitigation efforts per se adds a science requirement that we currently don't generally have. And so when we start thinking of future capabilities, they're going to need to be more sophisticated than what we have now to meet that challenge.
I agree that carbon science is basically an applied field, and that that providing information that's actionable is an absolute priority for the field, and it will shape the requirements for the observing system. And, I presented a sort of a two-part model. One, that monitoring emissions is incredibly important for influencing human behavior. And the other is that monitoring the biogeophysical carbon cycle is critical for knowing what climate we eventually get as a result of that behavior.
So I can, George, you and I can talk anytime, but I can talk to you in public here. I suspect that if the MRV work becomes central, which I think it will, the private sector is going to step into that. The very fine resolution satellites that we're getting now, you saw the tree counting efforts that are going on. That's exactly what's going to happen. It'll be a business. What we need to look at is the reliability and the veracity of the way that's done. And I think if we got into a partnership, a true partnership between NASA and the commercial assets, then the science could be behind that. So that's kind of where I was coming from before, but I don't think anyone's going to be waiting for NASA to launch the very high resolution satellite that we've been asking for. I mean, I did write a letter to the decadal survey and I did suggest that it be included, but it's not going to happen, you know? And you could say that that's good for American business.
Thank you, Paula. Frank Miller Carger, University of South Florida. I'm reacting to something that Francisco Chavez said, but also to many of the things that the other panelists mentioned, and that we have made these enormous investments in measuring physical properties of the earth and a lot of the biogeochemistry, and we continue to make these investments. And I think that we're doing that here because we want to understand impacts on life of climate and whatever we're doing. And yet, Francisco pointed out that the least developed observing system is that for life. And yet we don't seem to internalize that. And I think that that's been the topic of this week. But how do we move that forward? How do we move to an observing system for life?
Or is it, I think I tried to point that out. I'm not that familiar with terrestrial monitoring, but I think it's probably farther ahead than our monitoring in the oceans, but it will take significant investment to do that. And as I said earlier, I don't think I think it's going to become more and more important because I don't think I think that's what was said, that planting a few trees is not going to make a big difference to the CO2 problem. The CO2 problem, as far as I understand it, if we want to make a dent in it, they'll have to put things in the ocean, and so we'll need to know what those impacts are.
To give some hope, and as someone who came out of particle physics and astrophysics, we convinced Congress to spend close to $100 billion looking at subatomic particles and things at the primordial state of the universe. Earth science has got charismatic megafauna and other things going for it. I feel like it's just a messaging problem. If we can convince Congress the same way we did for finding a Higgs boson, to invest that level, they can.
I think the problem with the ocean is it's kind of out of sight, out of mind. You can you can convince people about what's happening on terrestrial environments because they can see it and feel it. And it's very difficult to convince a large fraction of people that what's happening in the ocean is absolutely essential for their livelihood. And it is a messaging problem, but it's a difficult messaging problem to overcome.
Time for one more question. Is that okay? And then we'll move to a wrap up, please.
Thank you. This is a question for Daniel. Thank you for your great talk. So we live in an unequal world where benefits and impacts of environmental change are unequally distributed. Power imbalance and dynamics are a key factor in the distribution of those benefits and impacts. So I'm curious about what is the role of power in the EVDT modeling framework that you are proposing?
I will share. Thank you. Really important question, especially because, in a sense, many of us do field work. How many of you do international field work where you go to a different country and you visit and you are a guest scholar? So I think we do have this question to ask as we are scholars, for example, from the United States visiting a different country. There's a form of power that we bring in our institutional names, the doctors and professors we bring with us as our titles. And I think it's actually so important. We can first ask for ourselves, what power are we getting implicitly because we come as a scientist to a country? There are important historical examples of scientists intentionally and unintentionally causing harm because they use their power to influence a local community. I try very hard when I'm working on a science project in a different country, first to go where I'm invited, actively invited by somebody there. Second, to have a local leader who I trust their ethical framework, and then I try to follow their advice on where to go, how to dress, exactly who to shake hands with and what to speak, what languages to speak. Sometimes I don't go to certain locations if it seems that my American presence would not be contributing to the local communities. But it's true that our world, so SDG number 1, right, is trying to address extreme poverty. One of the things we're not factoring in sometimes is the extreme wealth inequality. So as we talk about the different visions that Dave mentioned of like how the world will be rough, I want to just note it's going to be rough for poor people. And many of them live near the equator, and many of them are Black and brown. So some people will actually have a slightly more comfortable life in this new world that you described, Dave, but many people who are have experienced colonization, are indigenous, and have experienced different forms of economic exploitation will have the worst of this hard landing. So power is so important, and so that's another reason we need to both be carefully working alongside people that invite us to be there to get rid of some of our power when we arrive on these both local and international shores, and also ask, is it possible that as we do our science, I so much appreciated the question earlier about who shares what data on biodiversity, can we contribute to reducing power imbalances rather than making them worse in our projects? It's very, very difficult, and I think we'll make some mistakes along the way. And if we make some mistakes, we should then publish those and try to talk about how to do better next time. Thank you for asking.
All right. Thank you for the questions and the discussion. And I would like you to join me in thanking our speakers and visionary talks. So it was a wonderful session. I'm going to hand it back to Dr. Lorenzoni for the wrap up.
Thank you, Dr. Bontempi. All right, you made it to the bitter end. A round of applause for all of you for sitting around until today. We hope you really have enjoyed this opportunity of coming together as a joint community. I want to thank my fellow program scientists from the focus area and all of you that were voluntold to come and talk to us. We really appreciate it. You've been an inspiration, not just for us, but hopefully for your colleagues across the community. I have tons of questions I want to ask all of you. All right. It's done, but it's not over. We still have our poster session until 5. The posters are also going to be available online. And those that submitted posters or that have posters out there that have not uploaded them, you still have an opportunity to do that, which may be a really nice resource for those that either couldn't make it today or didn't make it to your poster. So again, thank you so much. We hope to see you again. Maybe it's not going to be 8 years. Maybe it's going to be shorter, but we'll figure that out together. All right. Thanks, everybody. Oh, wait. Oh, yeah. So, and I did mention it this morning, we will be emailing you something, aside from, I think, a survey. So again, we're always looking to see what worked, what we could do better. And your input is critical for us to make those positive changes. Thank you. Oh, wait. Okay. Oh, yeah. Okay. So focus here. Okay.